My name's Tom Lippincott. I got my PhD from Cambridge in 2015 studying computational linguistics with Anna Korhonen. And since then, I have been research faculty at Johns Hopkins University. And today I'm going to be talking about StarCoder, a general neural ensemble technique for humanities scholarship illustrated with the study of post-Atlantic slave trade. And this work is in collaboration with two historians, Jenny Williams, who's soon to be postdoc at UC Santa Cruz, and Professor Francois Furstenberg. This is an overview of the talk. I'm going to be skipping many interesting details for the sake of time, but I will include a link in the comments to an additional talk that will go into much greater depth and could potentially organize some sort of live Q&A session later in the week if there's interest. Okay, my broad motivation in working on StarCoder has been to bring advances in AI to humanists a bit more directly than they have in the past. So working in machine learning, there are some characteristic end users that we encounter quite a bit. So financial analysts, medical professionals, military analysts, journalists, they all have some things in common. So they're all concerned with specific domains and subdomains and esoteric questions about them. To answer those questions, they need to go out and gather and structure very targeted data. And once they have that data, they then need to explore and reason over it. Ultimately, they'd like to find and present some sort of coherent, interesting narrative. It might be a report that they write up for their boss. It might be an article in a newspaper. It might be a patient report. And they're doing all of this with a wide range of technical ability. This is very similar to how humanists are operating, with very esoteric questions on very targeted data. The big difference here is that humanists don't have large organizations behind them that are specifically advocating for and underwriting research for their benefit. So how can artificial intelligence help humanists? Well, scholars in the humanities are already capable of deep, focused reasoning. That's basically their training. But they can have preconceptions from centuries of received wisdom about how to think about their domain. It is possible for them to become deeply invested in supporting or refuting a particular conclusion. And just as a basic limitation of human cognition, it's not possible to attend evenly to a large amount of data or all the hypotheses in a hypothesis space. At the same time, artificial intelligence at the moment has very limited capacity for abstract reasoning. But part of its distance from direct contact with the data means that it's easier to avoid bias towards a particular conclusion. And at worst, we can make it so that the process is something that can be audited later to understand the bias. AI, of course, is also able to uniformly process large amounts of data and thoroughly explore hypothesis space simply because it doesn't get bored. It doesn't have wavering attention. And it can potentially produce things like well-formed probabilities or well-specified representations, things that are concrete, tie back to the data, and that humans can then look at and comprehend. So as I started thinking about these possible goals, I wanted to make a list of what a humanities-centric AI might look like. So some of the guiding principles. I wanted it to be minimally disruptive to existing practices. I didn't want humanists or computational researchers to have to dramatically change the way that they are currently working. I wanted it to be purely added value as much as possible. When it did suggest new behaviors or practices, I wanted them to be best practices, particularly with relation to data management. I wanted there to be additional benefits on top of the actual modeling process. And I wanted it to be unsupervised and exploratory. I wanted it to be looking at a more general space of question where it's just what is interesting about this data? What are the unexpected patterns in this data? Bring them to the attention of the scholar rather than drilling down into solving one particular problem. These are reflected in two more tangible design decisions. So the first was to focus on the boundaries between humanistic and computational research. And I see that as the data in and the hypotheses out. So if you look at the artificial intelligence as being somewhat of a black box, we wanted to be able to accept the data that humanists are already producing largely as they produce it, and then generate something that is somewhat intelligible, that fits into the kind of hypotheses that humanists would normally be interested in finding. And the other design decision was to start with a very simple core model that we understand fairly well, but that can be easily expanded with new machine learning architectures and so forth. So basically a place that computational researchers can plug into and try out new things without disrupting too much on the other side where the humanists are getting their hypotheses from. Okay. So to illustrate this, I'm going to talk about a particular study that began around the same time as I was thinking about StarCoder. So this was a study of the post-Atlantic slave trade, which is the massive reorganization of slaves when the United States shut down the Atlantic slave trade. So basically, the manpower within the United States was dramatically reorganized in response to this because there were not going to be newly imported slaves from Africa. So when I joined the study that had been going on for a couple of years, these scholars had been looking at shipping manifests, particularly between Baltimore and New Orleans. And they were doing something that was very reasonable. So a shipping manifest looks something like this. And what the scholars were doing was opening up a spreadsheet and transcribing the data. Right, so pretty straightforward. It's already essentially in tabular format. At the same time, they also had access to a large number of fugitive notices from the Baltimore, Virginia, so Maryland, Virginia area. And they were doing something similar for that. It's a bit less structured, but they were still able to pull out regular information from these documents. And when I joined, they had transcribed about 45,000 manifest entries, about 11,000 fugitive notices. So this is still not big data from a machine learning perspective, but in the back of my mind, I was thinking there are thousands of studies like this going on. And in fact, just in this particular space of transcribing records of the American slave trade, since starting this study, I've met a dozen or so other groups that are doing essentially the same thing. Different data, but they're transcribing it in very similar ways. So what might a historian want to do with this data? So this was one question that I was trying to get at right away. So the historians were interested in following one slave throughout their life, so creating a narrative for one individual, grouping owners according to the nature of their workforce, mapping out trade ecosystems, reconstructing slave families when there's no really identifiable information linking them together, and determining what drove valuation in transactions and rewards. But there are difficulties with this data as it was collected in the wild. So it's unnormalized. Tabular data by its nature is going to be recording many things many times. And this can have some serious problems. So if you are writing down if you've converted all of your escaped slave notices into tabular format, and then you ask a question of it naively, like what is the typical age of an escapee, that one slave that escaped 50 times is going to massively skew your results. And it's not necessarily going to be obvious to a historian working with that data that query has that problem. The data is noisy, so there are variant spellings in the data itself, and of course there are typos that are introduced by the transcription process, and sometimes exact data practices are not followed perfectly, and you get comments in line and that sort of thing. And then there are missing and underspecified entities. So the majority of slaves don't have a last name recorded. So that's kind of a pathological case where we can't really tie people together. So there's no way to tell whether two Johns who are listed in the data are the same person unless you do some very sophisticated reasoning over the data, pivoting between different rows and trying to figure out, oh, this person owned this person and sold to this person, etc. So spreadsheets like this are everywhere. I see them everywhere in the humanities, and I also see, beyond the humanities as well. It's a very typical first step in just collecting data. One thing about them, one important aspect of them is that they constitute, I think, an implicit entity relationship schema. So an entity relationship schema is a term from database theory, which is a very general way of representing arbitrary information as things that have properties and relations between things. So just to give some terminology here, there are field types. So things like, it could be text, it could be a categorical value, it could be a numeric value. And then there are fields, which are of a single field type, but have a specific interpretation. So like a name is a text value, but we also have more semantics about what a name actually is. An entity type is going to be a coherent bundle of potential fields. So an owner or a person could have a name and a job and a height and so forth. And then a relation type is a predicate that that ties entities together, right? So a child has a parent, that sort of thing. And then entities and relations and fields, they're all realizations of the concepts. So just to take some examples from the data that was being transcribed by Jenny and Francois, this would be what one of the rows might look like in their CSV file. And you can see right away that there are different field types. So there's numeric, there are categorical, there are text fields, and then there are even some more complex fields that have additional semantics in them, so things like dates and geographic coordinates. There are also entities here. I've highlighted them but I've also go by a naming convention here where the prefix is the entity type. So you can see that a slave is a bundle of slave name and slave age. And then there are domain-specific relationships. So again, this is one row of a CSV file, but because we know that we're transcribing, say, manifest records, we know that particular relationships hold between things that are mentioned on the same line, right? So we know that if a slave and an owner are mentioned on the same row, we know that they have a particular relationship. And if you take a data schema of the sort I just described and apply it to your data set, say your CSV file, you'll get some number of graph components where each component is a set of entities that are self-contained and linked to each other. StarCoder's native format at the moment is JSON linked data. This is still a bit in flux, but it seems to be the right balance between human readability and having the kind of necessary structure to represent entity relationship schema. So this is a subset of the schema for the post-Atlantic slave study. And you can see that it is, I think, fairly intuitive, and it lets the scholars kind of record their expectations and record their domain very carefully. And this is a rather simple example, but you can see that it's defining these 4 fields, that they have different field types. Then it defines the entities in terms of the fields, and it defines relationships or potential relationships between entities. Okay, on to the actual model, StarCoder, and deep learning for the humanities. So the way StarCoder is going to work is it's going to take a data schema like the one that I just showed, and it is going to generate a model that in some sense matches the data structure. And it's going to use several building blocks to do this. The first is a collection of related building blocks called encoder, decoder, and autoencoder mechanisms. And these are going to be used to capture the entities and the fields. Then there's a graph convolutional mechanism that is going to be used to capture the relationships. And the reason that the whole model is called StarCoder is because I got sick of saying encoder, decoder, and autoencoder. Okay, so this is going to be a very brief introduction to what I mean by encoder, decoder, and autoencoder. This is a very simple, what's called feed-forward neural network that I'm just going to use to illustrate things. So there's some input data that comes in. It's represented in some numerical way. It's passed through several transformations. These are called hidden layers. And then the very last hidden layer is used to perform some sort of task. Okay. And that task could be something like, let's say, classification. It's saying good or bad, maybe. It's going to determine whether it got that right. It's going to compute something called the loss function, and then it's going to send that signal back through the network and update various weights, tune things, and then repeat the process again and again, and that's how training will work. The narrowest layer, in this case, it happens to be the last one, but it doesn't have to be, is called the bottleneck. That's the narrowest layer in the entire network. And the intuition here for calling it that is that to perform the task, whatever information is used to perform the task needs to be represented through each of the layers, and therefore the narrowest layer is a upper limit on how much information can pass through the network. So by the time you get to the narrowest layer, the model has to be able to very efficiently compress or summarize the information to fit it through just those two nodes. And so presumably it has learned a lot about the data by that point. And that representation is very information dense. Now, if you chop off the task, say you've trained the whole model, you can throw away the final task that is being performed and just have something, now you just have something that takes data in and turns it into a very dense representation. Okay, and that's called an encoder. You can also go in the opposite direction. You can take a very dense representation and have a model that tries to unfold it back into some sort of output data. And that's called a decoder. Encoders and decoders are often paired together. They're often components of the same model. A classic example would be something like machine translation. So if you imagine the left-hand green is an English sentence and the right-hand green is a French sentence, and the orange bottleneck in the middle is some sort of deep semantic representation of the sentence, kind of like in the Chomskyan sense, then this would be like sort of like machine translation, right? So it's encoding the sentence into a language agnostic universal, and then it's decoding the sentence back into the target language. But you can also set the input and the output to be the exact same thing, in which case the goal is to just reconstruct the input. And this is called an autoencoder. And the metaphor I have on here is something like one person learns a topic very well and compresses that information down and writes, cliff notes or shorthand version of it. Another person learns how to interpret that shorthand, and so that when they're handed that little notepad, they're able to expand it back into the full original information. So just to summarize, encoders transform the data into a very dense fixed length representation. A decoder takes such a representation and generates something else, maybe data. And an autoencoder learns how to preserve a representation through a bottleneck by a combination of both. Okay. graph convolutional mechanism, I'm not going to go into detail on that here. I will in the appendix. But it extends traditional convolutional mechanisms, which operate on grids. They're often used for things like images. But in this case, it's going to let information flow between related entities in StarCoder. And essentially, every graph convolutional layer that you add to the model allows each node to see one further hop in the structure. So StarCoder is going to use those building blocks in combination with the data schema provided by the humanist to generate a tailored model. So first it will read that data schema so that it knows what field types, entity types, and relationships it's going to be modeling. Then for each field, it's going to allocate appropriate encoders and decoders. For each entity type, it's going to allocate an autoencoder. And each autoencoder is going to use a GCN-like mechanism to incorporate adjacent bottlenecks across the graph structure. And here's a visual of what I just said, but for a particular instance. I won't go into too much detail here. I will in the appendix go into much more detail. But just some things to note here. So this is saying that we're looking at the model as it's being applied to a single entity, John, a 23-year-old slave. You can see that StarCoder has chosen particular architectures for each field. So a recurrent neural net for a text field, identity just for a number, embeddings for a categorical. And it's concatenating the various encodings. It's going through an auto-encoding mechanism here. It's pulling in the bottlenecks from adjacent entities, which are being computed in parallel, summarizing them and propagating them to the second layer of autoencoding. And then at the tail end here, you can see the decoders at work, where they're taking this the final representation of the final autoencoder and trying to reconstruct the original entity. So how can we use a trained model? Well, those bottlenecks are a big part of it. So the bottlenecks in the final autoencoding layer can be used to compute similarity between entities, and that gets you quite a bit of mileage. So you can do things like finding clusters of entities. You can do things like information retrieval, find me more of similar things, and so forth. The model can also be used for field generation. So you can mask out fields within an entity, or you might just have an entity that doesn't have information recorded for something like the slaves that don't have last names, and try to generate likely values of that missing field. You could also use it to detect improbable values of a field that is there. So this would be kind of like anomaly detection, maybe trying to correct noisy data. So you look at, say, a distribution for a categorical value, and if it has high entropy, maybe that's a problematic one. And you can do things like observing the response of one field to another. So interactively, you could go in and start turning a knob on one of the fields, like say you took John's age and started ramping it up or ramping it down, and seeing what happens in terms of predictions for the other fields at the other end of the StarCoder model. Okay, on to results and ongoing work. Once we had trained a model on the post-Atlantic slave trade data, we took a very simple approach to presenting the output to the historians. For each entity type, we gave them a list of entity pairs that were most similar to one another. And this brought a number of things to the surface. First of all, the model picked up on mistranscriptions pretty readily, and this was a large amount of the similarity derived from small alterations like this. More interestingly, the model picked up on semantically equivalent variants that did not have a lot of string overlap. So essentially what this is saying is the model believes that using the expression New Orleans is essentially identical to using the expression Louisiana. They're interchangeable in this data set. The most interesting results came when we looked at the slave entities. So the assumption had been that this was a one-way trip from Baltimore to New Orleans, that it was a one-time reorganization of labor, and that slaves were sent into the interior of the United States from New Orleans, never to return to the Northeast. But we were seeing that some slaves were being sent again and again and again from Baltimore to New Orleans. The records, the entries for them were different enough that they were not considered exactly the same, but the model was able to determine this by comparing the bottlenecks. So the first hypothesis from the historians was that this is some sort of leasing, perhaps for seasonal work, that sort of thing. But you'll also notice these are the top four entities, the top four most similar pairs of entities of slaves. These are all young women. And so taking it a step further, a hypothesis here is that this is some sort of sex trade. And neither of these things, particularly the latter, were on the radar of the historians when they were looking at this data initially. So these are rather dark conclusions, or dark hypotheses, but I think very exciting that we have an unsupervised model like this that is able to bring this kind of information to the attention of a humanities scholar. And so I'm excited to see what it's going to do in other studies. Speaking of which, there are quite a few ongoing studies and data sets that are being run through StarCoder right now. I will go through these in detail in the supplemental video, but I just want to flash this up here to give an impression of the breadth of domains that are being used to guide the design of StarCoder. Thank you for watching. As I mentioned, there are links in the description to these slides, to the supplemental presentation that goes in more in depth, as well as a couple of GitHub repositories.